Welcome to today's webinar titled Designing for DDR4 and Beyond, brought to you by Keysight Technologies. This webinar is part of the Keysight Engineering Education Series. I'm Carmina, and let me introduce today's speaker. Stephen Slater leads the Signal Integrity and Power Integrity Product Planning and Marketing team in Keysight Technologies. Over the last decade, Stephen has worked closely with customers using Keysight's advanced design system for high-speed SerDes channel simulations, DDR simulation, and electromagnetic simulation for PCB applications. Before joining Keysight, Stephen graduated from Griffith University in Australia with a Bachelor of Science in Electrical Engineering with first-class honors and a Bachelor of Science in Information Technology. Welcome, Stephen. The floor is yours.
Thank you very much. It's an absolute pleasure today to be talking to you about DDR. And what we're going to start off with is posing the question of why does memory system design actually matter? And then we're going to take a look at some of the top challenges that face memory designers out there. Taking a bit of a background into what's changed from DDR3 into DDR4, and then what are some of the characteristics and features that we expect of our EDA tools in order to evolve with the change in technology. That will segue nicely into about a 5-minute demonstration of our Pathwave ADS Memory Designer, something that's just been launched and introduced. And then we'll round out today's presentation with a discussion about the future, the modeling ecosystem required for DDR5. Okay, so let's get started. For a bit of fun, I'd like to start off with a poll. I'd like to invite you to think about your own customers and think about the products that your company makes as well as your company itself, and consider which of these items in the list actually contribute to generating customer loyalty. So please tick any and all that apply, and then we'll give the poll results at the end of the presentation. Okay, thank you, and let's move to the next slide. Thank you for the responses. We'll wait until the end of the presentation to collate the results and give feedback. But firstly, I want to point out price. Should price really have been on the list? Because typically when we think about the value we create for our customers, we tend to put it in the perspective of, well, it's product performance or product features versus price. That's what provides value to our customers. But actually, the way we should look about customer loyalty is that really it's all about the value that we can create versus the value that our nearest competitor can create. If we take all of those items from the poll and distill them down into 4 distinct categories, then these are the ones that I chose. And what we want to do is if we want to create loyal customers, we need to work out how we can maximize each of these to our advantage. What you see here is the same thing but organized in a Maslow's hierarchy. And what you've got is on the very base layer, that's the foundational element. Without that, you don't even get to be in business. But then on top of it, you have a next layer which sets differentiation between yourself and your competitors. So the first layer creates just satisfaction with the product. The second starts to create customer loyalty. And then the third, the very top of the tree, that helps to create actual champions for your product. And you can think about that. Think about the last time that somebody suggested to you, oh, you definitely should use this company or purchase this product. Many of the times it's because it performed well, and on top of it, they had an excellent purchasing experience or an excellent experiencing with after-sales service or support. So how does memory design impact this pyramid? Well, the reliability part is fairly obvious because if we don't do a good job on the memory design, we can end up with failures in the field, and that's going to impact the brand and the reputation of our products. The next one is that in the performance and usability, we have the chance to design for a differentiation compared to our competitors. We can offer wider bandwidth and end up giving greater performance. And then at the very top level, easiest way to think about this is for those companies working on semiconductor products, ICs, where providing design references, design guides, workspaces, and the ability to help troubleshoot their customers' implementation of a memory design ends up being extremely valuable, helping them to get through the most difficult parts of designing at the cutting edge. Inside Keysight, we have many hardware engineers, and I was lucky enough to interview 2 that work on very high-speed PCBs. Firstly, Cameron McKay, I asked him about his DDR development, and he said to me, well, the fastest I can develop a DDR interface that operates with a low bit error rate, then the faster we can get a reliable product to market. And anything that shortens that development time means we get our products to market sooner. And likewise, another snippet that I took from Rick Rabinovich, who's a senior SI engineer in our company, said, well, I believe that design should be done at my desk before the hardware is built, and that the lab is the place to verify and not to design. There's two interesting perspectives from different teams within our organization. Okay, so next we're going to move on to what are the top challenges for designers. So to begin with, memory design is already very complex. If you were to compare it to something like high-speed serial, the difference is that there's just so many more nets. And not only that, you've got in the read direction and in the write direction, so different simulation setup. And for the cases of a server, then you might have multiple slots per channel. So it's a different SI problem if I've only got one of those slots populated versus whether having two slots populated with DIMM cards. After we've done all the simulations, then we get to the point of needing to collate the results and trying to glean some insights from them. And then also, as we move from DDR3 into DDR4 and then into the future, we are ending up with much less design margin. So timing margin is shrinking, voltage margin is shrinking. And the final point of DDR design is that it's inherently very difficult to troubleshoot. So once you've got a first prototype and you discover an issue, it becomes difficult to understand why. So we want to catch as many problems as we can during the design phase. Otherwise, we risk slippage of the schedule or worse, product reliability issues. Now, when I travel around to see customers, it's interesting. The typical questions come out often about EDA software. The questions that they'll ask is about accuracy. They say, well, how accurate are your tools? And if we distill that down into really what the customer's desire is, it's, can I predict my margin accurately? Next thing they ask is, well, how long does it take to simulate? And the driving behavior behind that is, well, in DDR, I've got so many things I need to simulate, so many corner cases I want to sweep. Can I simulate everything that I need to in a practical amount of time? And then finally, the most challenging one is troubleshooting. So I've got many different signals, and I want to be able to understand what's wrong. Can I avoid issues before we get through to manufacturing? So can the simulation provide me with an accurate mental model of what's going on, such that I can use it to troubleshoot issues that I may find later on? The question you might ask is, how is DDR4 different to everything that's come before it? Well, firstly, the thing that we're trying to do is reduce the amount of power consumption. And secondly, we're trying to go much faster than we did before. Now, one of the ways that they managed to reduce power consumption is by dropping the voltage rails. And next, they moved to a pseudo-open drain style topology. So as you can see on the right-hand side here, now the receiver is always tied to the high voltage rail, except when you drive a zero, and that's when it's pulled low. So current only flows when we're driving zeros. The next thing they did is they used a feature called data bus inversion, and that means if you look across, say, a byte lane at 1 unit interval, if there's more zeros across that byte lane than there are ones, then what they do is they flip all of the bits. So the ones become a zero, and to flag that they've all been inverted, they use the data mask line. That now becomes the DBI indicator. Something else changed in DDR4, and that is, as the voltage and timing margin started to decrease, JEDEC needed to take another look at the way that they specified setup and hold times. And actually what they intended to do is to move away from setup and hold and specify instead a receive bit error rate mask. Now this is something like what you might have seen in high-speed serial technologies. So effectively we've got this mask in the middle, and what we need to do is provide it with a signal that stays outside of the mask. So it's a much simpler definition of DRAM requirements and for system design. And also it gets rid of the need to do any of the slew rate derating that was necessary. So basically, depending upon the speed grade and the slew rate, you would have to choose a different setup and hold time. All of that is done away with in the new spec. But this is a fundamental paradigm shift for DDR4. Now, if you come from a DDR background, then the idea of a mask might be quite new. So effectively what we're saying is, inside of the DRAM, there is no perfect timing instant or perfect VUF. There's internal jitter and there's internal noise, meaning that the sampling instant is moving around everywhere inside this yellow box. Now, effectively, if we stay outside of the box, so if the signal, the input we provide stays outside, then there's a contract between the DRAM and the system vendor that the DRAM will have a bit error rate of 1e to the minus 16 or better. The mask is an interesting new idea, but one of the things is that timing margin becomes further eroded by ISI and random jitter. As you can see in these two scope displays below, if you have just 13,000 bits captured, it looks like there's plenty of margin to mask, but that mask is specified for 1e to the minus 16. If you put 1 billion bits through, that margin to mask is much further reduced. But how much margin do I have at 1e to the minus 16? To prove the point a little bit further, we have to ask the question, well, how important is jitter to knowing your real margin? Here I've got an example of a PCB that's been extracted on this XILINX evaluation board, and we used our SIPro EM simulator to extract the model. Then here you see you've got the ultra-scale FPGA and some DDR4 DRAM provided by Micron. So if we take that EM model and put it into a DDR bus simulation, this is just a short channel and it has ideal TXIRX around it. So in the first case with no jitter at DDR4 speeds, we see that any eye closure is just due to ISI from the channel. And then at the bottom, you see when we have random jitter turned on at 2% of a unit interval, what we're looking at is the red bit array contour, and that shows us exactly how much eye closure we're expecting at 1e to the minus 16. And you can see for DDR5, there's the case that there's 47% reduction in timing margin, which equates to about 27 picoseconds less margin to the mask. So, are you simulating today with SPICE and a worst-case bit pattern? Because as DDR speeds reach the top end, there's many more bits in flight, there's more crosstalk, and determining the worst-case bit pattern that will give you the maximum eye closure becomes more exceedingly difficult. And not only that, it doesn't account for the long tail of the random jitter. So, without something like a DDR bus simulation, are you designing with your DDR eyes wide open? The next question that we'll tackle is how important is crosstalk to knowing your margin. So we return again to the same example of the XILINX board, and then we pass it through into SIPro for analysis. Here you can see the data nets that we're going to be analyzing. And this is what we came out with. So just taking a look at one of the particular lines and then looking at all of the near-end crosstalk and far-end crosstalk for that particular data line, we see that where the marker is placed, after about the Nyquist frequency for DDR5 4800, we see that we've got high flyers of DQ4, DQ6, and DQ11. When we look into the layout, we can see some potential reasons why the DQ4, DQ6, and 11 happen to be the highest crosstalk neighbors for the victim DQ2. So we've got some regions where the vias start together and end together, and then we've got another section of trace where the signals spend a bit of time running parallel to each other. Now, one of the interesting things, which is true of all DDR, is that you usually have more signal pins than you do ground pins. And so we get higher crosstalk because we have one ground return pin that's being shared by multiple signal pins. So then if we take a look at putting the channel into the DDR bus simulator, you can see that at DDR4 1600, again, we have no jitter and no crosstalk, just ISI from the channel. And then if we turn on the adjacent neighbors as aggressors, there's no jitter, just crosstalk. We see how much additional jitter and additional noise that's added into our signal. That actually equates to a 58% reduction in voltage margin and an 18% reduction in timing margin. And again, these were simulated with a DDR bus sim. This leads to another very poignant question, which is, does your PCB extraction tool today correctly model the via-to-via coupling? And does it capture the signal return current path accurately? Because, as we've shown with this, anything less than a pure EM approach may be misleading you, especially as we approach the higher speed grades of DDR4 and moving into DDR5. So let's put it all together and take a look at both jitter and crosstalk on the channel. So running at the fast speed of 4800, you can see that we get 64% reduction in voltage margin and actually nearly exactly the same reduction in timing margin. Now this is with the ideal TXIRX that we've been using, and therefore it has the appropriate rise and fall times for 4800, but it does not include package effects, and it certainly doesn't include any of the other nonlinearities you might find in a standard voltage versus time waveform of an IBIS model. So the next question you might ask is, what happens if you do apply an IBIS model? Well, we don't have models for DDR5, but you can apply a DDR4 model and try to overclock it. And the very first thing you'll see is that, of course, you get a very closed eye. But it's interesting because it gives us the opportunity to try to determine if with equalization, maybe the eye can open up again. Okay, so now we're going to move into a section where we're going to talk about what do we really want or need from EDA tools in order to be successful with memory design. Now, if you can cast your minds back to the start of the presentation, you remember we talked about some of the complexity of setting up these simulations. So really what we want from an EDA tool is to cut down the amount of engineering effort. So can we get to a setup time that's just minutes? Can we have one schematic for different types of simulations? Can I use groups of signals and apply IBIS model to them all? Can I do simple wiring and connectivity? So use information from the layout in order to help me connect to my IBIS file. Can I just use one single test bench that I can do both pre-layout and post-layout on the same test bench? And when I set up my EM simulation, is there a way that you can guide me through it nice and easily? And then when it comes to having the most accurate simulations, I need to be able to capture effects like crosstalk. I need to be able to predict the eye closure due to jitter. And finally, when it comes to measurements, please don't ask me to set up those measurements individually per line. I want to be able to take a look at groups of signals at a time and apply the measurements correctly. So I'm very pleased to introduce to you our solution to many of the needs that were presented on the prior slide. So this is Pathwave ADS Memory Designer, and as you can see, it's an abstracted view. So we're looking at a top-level, system-level design where we've got bus wires that connect a memory controller to a PCB out to DIMM connectors and to individual DIMMs. The memory controller, you assign your IBIS models directly as groups. We use information from the layout to automatically connect pins from the PCB to the memory controller. And we've got a brand new memory probe that gives you access to each and every signal inside each of the DDR components without needing to wire anything up. So let's take a look now at a pre-recorded video demo of Memory Designer in action.
Let's begin our demo by taking a look at the final objective, which is the ability to be able to assess each of the data lines for signal integrity, being able to see how much eye closure we have, being able to plot things like the DQ to DQS skew, and then using many of the powerful features built into ADS data display, like measurement equations and the ability to do post-processing on the traces we see. As you may remember, this board was first extracted with SiPro. And this is what SiPro looks like. You can see it's got a modern 3D user interface. And we've added a new DDR setup wizard. Here you specify the speed grade or the rise time, and it will set the max frequency accordingly, as well as the sweep plan. And then we go and interactively select the memory controller and any of the memory devices that we're going to connect to, and it will determine which nets are connected between them. So it's not easy to forget anything. And then you can go and deselect the ones that you don't want to simulate this time around. And then when we're done with that, we can hit the Generate Setup button, and it will add this analysis to our workspace tree. A massive time saving is the fact that the setup wizard automatically creates EM ports. So here the plus pin is placed on the pad where the component is connected, and the minus pin is the closest ground pin. Now we also created a DDR attribute editor, so once the EM simulation is finished, we can then go and save information into the S parameter file, information that Memory Designer can later use. So for instance, the information we can use is the reference designator of the individual ICs and the net names, which can be parsed into a signal type as well as a signal index. And that's the information that we use back in schematic for Memory Designer to make the automated connections. Now we're back in schematic, let's go and place down the SiPro generated cell. And it's going to use the S parameters as well as bring forward the reference designators and signal IDs, which we can use to connect to the DDR controller, the memory controller. So also place down a memory probe as well as a block for the memory devices. And now let's push in and instantiate the memory controller. First step, we're using those signal IDs that we had before. Next, we have to grab the reference designator we care about and turn it on. Then we can browse to our IBIS or EBD file. And then now from inside, we get to select, well, which of these signals do I really want to simulate? Then we move over to the Model Setup tab. And here now, we're going to choose what simulation type. So that's going to change the stimulus source, and the speed grade, and then we assign our models as a group to those signals. Since we use the same reference designators and signal IDs in both of these blocks, making the connection with the bus wire is as simple as just pressing one-click Auto Connect, and the connection is made. Now let's take a look at the memory device, because the memory device is a little special. It could be represented as a single DRAM or multiple DRAM or even an entire DIMM. We have that capability to enable that level of abstraction. So once we've set up the simulation mode and the direction of simulation, whether it's read or write, then we can move into the model selector and choose which particular on-die termination model we want to use. And you can see by the field model alias, we have the ability to specify a variable that we can go through a batch simulation to sweep those values. Okay, so finally now we make the connection between the memory device and it's one click and we are done. So let's move into the memory probe. It's a universal probe, and it means it gives us access to every single signal inside those DDR components. So I can select individual signals that I want to add, or I can add them all as a group. And then the measurements, I can select the measurements and apply them as a group, or I can set them individually if I choose to. Then when we move to reference signal, this is where the memory probe makes an intelligent decision about which strobe relates to which DQ, So if I want to do something like a strobe die, it would automatically have that set up for me correctly. If the memory probe is set to perform compliance tests, then what happens is we invoke Keysight's Infinium offline software. It's exactly the same software as what you would use on a scope to make measurements on a real signal on the bench, but ADS completely automates and controls the Infinium software and the DDR4 compliance app. So here the DDR4 compliance app is making measurements, and you see that for one of the measurements we have a small amount of margin. And then it records how many measurements were made, the standard deviation for those measurements, and also on which line we had the worst amount of margin. And it shows us that for the DRAM chip U60 on command address 11, this is where the smallest amount of margin was recorded. You can see that clicking on the waveform, it shows you exactly where in the waveform that measurement was made, the one that had the worst amount of margin. And next, we also get a complete DDR4 compliance test report, where all of the measurements that were selected are then generated as a PDF report. And this could be used for documentation for detailed sign-off.
By using the same environment for simulation and measurement, it means that making the comparisons become very easy. And in doing so, it gives us renewed focus to try and find and eliminate discrepancies between simulation and measured data, improving the models for next time. Pathwave ADS Memory Designer provides us with a very predictive workflow, giving us visibility of our margin down to very low bit error rates. It also takes productivity to new highs with the new level of abstraction we've provided in Memory Designer. And finally, it provides deep insights by allowing us to use automated DDR4 compliance tests, which is exactly the same as test and measurement equipment we'd use on the bench with real prototypes. Now let's round out the presentation with a look at the future of DDR5 and what's needed from the modeling ecosystem in order to support the new features. So the first thing to note is that DDR5 is not a ratified spec as of yet, but we can talk about perhaps some of the equalization possibilities. And this is something that's new. For the very first time in DDR5, the DRAM will have equalization such as a 4-tap DFE and an adaptive gain block. Now, this equalization is likely to be controlled via the mode register on the DRAM. So the controller, the memory controller, will contain complete control over moving through the different equalization presets in order to find the best combination of equalization on TX and RX. However, you don't need to wait for DDR5 to be ratified. You can already start exploring designs today. All it simply means is we need to document some of the assumptions that we make when we take one of our existing DDR4 designs and try to move it forward to DDR5 speeds. So firstly, we take a look at things like rise time and fall time and how we think those might change. We document our assumptions about random jitter and deterministic jitter. We also take a look at the DRAM model itself. Here we have the ability to represent 4-tap optimized DFE inside the receiver block, where the simulator will actually take a look at the impulse response for the channel and calculate an optimized set of taps for DFE in order to open up the eye. So we begin with a server case study example. It's taking a design from DDR4. It's a pre-layout study where we've got 2 slots per channel populated with 2 DIMMs. And there's 8 lines that are data and 1 differential pair, so 10 lines in total. And here what we do, we look at 12 different corner cases, where the corner cases cover things like the different lengths of transmission lines, min and max impedances for sections of the traces, as well as things like on-die termination and rise time, fall time for CPU. The results of the batch simulation show that out of the 12 corner cases that are run, there's actually 5 of them that have significant margin to mask. So the reason is that the DFE is actually able to clear up much of the intersimple interference in the channel, even at such a high speed as 4800. So this gives us very good information about what to look for and what some of the constraints that we might put into our server design as we're designing for those really fast speeds. The other thing that's important to note is that this is with AGC turned on, and that's one of the interesting things is that with AGC now, well, we often know that there's a trade-off between voltage margin and timing margin. So when the AGC boosts a signal that has lots of timing margin, then we are also amplifying the noise as well as the signal. So this is an interesting way to take a look and find which one of these actually has appropriate margin to move forward. As we move from DDR5 exploration into DDR5 real product development, we need to swap out the TX and RX models for more accurate representations. That means we need to get the real model from the silicon vendor. Now, IBIS AMI has been used for quite some time to encapsulate equalization and some of the nonlinear and time-varying effects that you find inside a receiver. But the difficulty is that IBIS AMI was always designed for differential signals, not single-ended signals like we find in DDR. So there's some aspects, like DC offset, for instance, that are not part of the IBIS AMI spec to date. And what we need to do is evolve the standard so that these models can pass in the VREF into the model, so that inside the equalization they can use that VREF for performing some of their equalization and passing out a signal that is correctly scaled with the right voltage swing. The second topic concerns asymmetry of the eyes. Here you see with pseudo-open drain topologies, if you go from a transition of 0 to 1, it presents a certain impedance to the channel, but if you go from a transition of 1 to 0, that impedance is different. And so therefore you get a different rise time and a different fall time. At first glance, these eyes look exactly the same, but I invite you to take a look at the crossing point. You see that on the left-hand side, the crossing point is much higher. And what this means is that that is where the mask would be centered across this VREF, and the bit error rate contour would be quite different, and the margin to mask would be very different. Now, luckily, in the DDR bus simulator, we already handle this asymmetry. But when you move to an IBIS AMI flow, the reference flow actually only allows passing a single impulse response to the receiver model. So it's up to the simulator to come up with innovation in order to deal with this, or else we change the input to the receiver so that you can pass two different types of impulse responses to it. The final topic is clock forwarding, and this is interesting because in high-speed serial you have a clock and data recovery circuitry inside the receiver. But in single-ended DDR5 you have an external clock, so the DQS would need to be passed into the IBIS AMI model. And one of the reasons why we present that you need to pass in this additional waveform is that because internally, through the package and then onto the die, the DQ path length is not exactly the same as the DQS length. And so therefore the jitter can become uncorrelated. Another thing that can happen is that the memory controllers themselves have the ability to optimize the strobe sampling instant. So they can kind of interpolate along the waveform and find a more optimal trigger point, a more optimal sampling point for the eye. So in summary, I hope that you've enjoyed hearing about the transitions from DDR3 all the way through into DDR5, some of the challenges and the reason why memory design matters. And then I was very pleased to be able to give you an introduction to our Pathwave ADS memory designer. And now we're going to pause and pass through into Q&A.
Stephen, this question comes from Gary, and let me go ahead and grab this question. What if we don't have an IBIS model for the controller?
A great question. Yeah, so in the presentation and the demonstration, I only showed us using an IBIS model. But in many cases, if you're working with particular CPU vendors, you might find that there's not an IBIS model that's provided, but you might get something like a HSpice netlist. So that's okay. ADS can work with the HSpice netlist. We will just create a transmitter or receiver block from that imported HSpice netlist, and then you could use that together with the DDR bus simulator.
Great, thank you. Here's a question from Stephanie. You showed examples of EM models for the channel, but do you perform early DOE types of analyses?
Yeah, great. So what I might do is I'll just push us back to one slide to talk about that. So in this slide, so just wait for it to come up. Okay, so in this slide, this is actually a case of what we call pre-layout exploration. So you can see for each of those individual pieces, those blocks, they each have variables for things like width and spacing of the traces. But in fact, instead of doing a continuous sweep over all of those different variables, you have to break the simulation space down into smaller pieces. So we tend to do things like, well, what would be a minimum impedance corner, a maximum impedance corner, and then a length like a short, medium, or long length for each of these particular traces. And then doing the same for corner cases for the silicon as well. So in particular for things like IBIS models, you've got a fast and slow model corner, and it's very appropriate in pre-layout to try to sweep through all of these. In fact, you just use a batch simulation in order to do that, and then take a look at the particular figure of merit. Actually, there's something which is, I should point out for DDR, it's quite complex, is that you've got multiple different topologies. So for instance, this server design, we could have both of these DIMMs populated, or we could just have one of the DIMMs populated, and that's a completely different signal integrity problem. And then not only that, but you've got read direction and write direction as well. And then we've got for command address lines, control, and data. So it's a very big simulation space to sweep, and we need to approach it with a simulation strategy to make sure that we get good coverage and we compute exactly how much margin that we have. Okay.
Great. I remember you did a poll earlier in your presentation.
Yeah. Thank you. Yeah, I think we've got the results of that now. So let's bring that up.
And while Stephen's bringing that up, please keep entering your questions.
Yeah, great. So this is interesting. So let's take a few moments to have a look through and see how did what you selected be represented here. The first thing is you've got quality, reliability, and performance. They're definitely the top. But then also we see that technical expertise, came the very next, as well as after sales service. So I think we kind of we're all in the same alignment that definitely quality and reliability very important, then performance, and then the technical expertise and after sales service. And of course we already mentioned about price and how price affects the perception of value, but really price is set by your position in the market. Okay.
Great. Stephen, here's your next question. This one's from Nicholas. What was a crosstalk measurement? Next, Bex?
Oh, yeah, sure. Well, let's go back to that particular
a little bit
slide.
earlier in the presentation. Mm-hmm.
Yeah. So here we go. Push this slide. Okay, so in this particular graph, this plot here, when you're taking a look at EM of the channel, this is taking a look at a subset of the S parameter matrix. And in this case, what I did is I plotted all of the near-end crosstalk. So that's a definition here of near-end for me is all of the other data lines that started on the same IC, and then also plotted far-end crosstalk, which is all of the neighboring data lines that ended up on the same IC together, and looking for the ones which had the high flyers. Now, when we come to actually running the DDR bus simulation and move to Let's move to this slide. Okay, so for instance, when we looked at this one, now you could also ask the same question: were these near end crosstalk? Were they far end crosstalk? Well, so along the data bus, you're either always transmitting or all receiving at the same time. So your nearest neighbors are likely to be, if you're transmitting, they're going to be transmitting too. So in this case, it's near end crosstalk which is being excited. Yeah.
Great, thanks so much, Stephen. Here's a question from Anmol. How do you separate crosstalk, ISI, and jitter in your simulation?
Yeah, great. Actually, this slide probably still talks to that same question. This is one of the beauties of simulation. One of the things that allows you to do is to be able to choose what you're including in the simulation. So, for instance, if I don't put in any numbers for random jitter or deterministic jitter, then I can simulate jitter-free. Likewise, when it comes to crosstalk, if I don't put in any of the crosstalk neighbors, if I just simulate without them, then we don't see the impact of crosstalk. And the final thing is about ISI, which is mostly due to mismatch in the channel. One of the things that you will see is that actually you get some degradation just by having even your nearest neighbors unterminated. So if you don't terminate those nearest neighbors in a representative load, then you'll find that actually you get more ISI just produced in the channel. So this is very easy to do in simulation, and this is one of the reasons why having a very good mental model of your complex system based upon a simulation, it means it's great for troubleshooting later on. So when you experience something on the bench and you're not sure why you're seeing what you're seeing, you always have theories about what might be causing that problem. You can come back to your simulation and experiment to see really what is likely to be the biggest contributor.
Great, thanks. Here's a question from James. Does Pathwave ADS support LPDDR4 and LPDDR4X?
Yeah, that's a great question. So this is the very first release of our ADS memory designer. So for instance, our solution for DDR has been around for many years. Our DDR bus simulator was released in 2015. But the demonstration that we showed with the nice new overlay, so maybe I can take us back to this one. Oh dear, sorry. That's not what I wanted to do. Yeah, so this one, this nice new usability overlay memory designer, which then connects to Keysight's compliance apps, that is being released 1st of March, and what will happen is we'll support DDR4 and LPDDR4 in this initial release, and then we'll look to add further support for things like LPDDR4X later on. But essentially, it shouldn't be very difficult work to add that in as well.
Great, thank you. Here's a question from Albert. Is the simulation bit by bit or statistical?
Yeah, great. So for that particular part, the DDR bus simulator is a statistical simulation, and then when we start to talk about what's going to be needed for DDR5, then inside the equalization, you can expect that there could be things like you've got a variable gain amplifier, and that might need to be adjusted. And also there's some other aspects of how the DFE or an interpolator on the sampling instant might adjust. So there's definitely things in DDR5 that are coming that are time varying or have some nonlinearity, and so that means that the DDR bus simulation needs to be moved to a bit by bit type simulation, and that's something that we're definitely working on right now.
Thanks. And here's a question from Ritik. Is ADS able to do power-aware simulations? I didn't see a VRM block in your high-level diagram.
Oh, great. Yes, so the short answer is absolutely it can be. All you need to do is you provide another blocker connection into the PCB that's representing behaviorally the VRM, and then likewise your PCB should be extracted with the decaps already as part of the EM simulation. SIPRO can handle that, so SIPRO can extract all of your signal nets and power nets and decaps all together. We saw that in the demo. But likewise, some people will actually extract the power plane separately. And there what they'll do is they'll extract the power plane as a separate PCB model. And so in this graphic that we're looking at right now, you'd have two different PCBs, one for the power planes and another PCB for the signal lines, and connect them all together. Now there's one more thing that I do want to bring up about this though, which is we talked about DDR bus sim being a statistical simulation solution, and even when we move to DDR5 with IBUS AMI models, that also is based upon the idea that the channel is linear and time invariant. And many of the types of simulations you do with for power awareness, things like synchronous switching noise, those tend to be they're most definitely time varying. So you might have a question in your mind: how am I going to do these types of simulations for DDR5? And actually, there's some recent publications from DesignCon where they look at running transient simulation to look at how much additional random jitter, how much additional amplitude noise as well as jitter is created by not random jitter, deterministic jitter is created by the power aware capability, and then being able to model that and add that in as a stimulus into your bit by bit simulation. So I definitely think that this is still an important challenge, something that needs to be tackled. But there is technical papers already discussing how these things could be modeled and applied for DDR5.
Great, and here's your question from Ron. How do you check with your tools the difference in signal length?
Oh yeah, great. So one of the things that's important to note is that when you just take a look at the trace length and the layout, actually what you really want is to be able to look at electrical length, and this is that's quite some years ago now. We had a good video where we explained the difference between doing switchback routing and serpentine routing, and actually you end up with two different electrical lengths. So the physical length is exactly the same, but the electrical length was different. And so therefore, the key thing that you want to do to make sure that things are time aligned is to look at a measurement of skew. So we have that built into the memory probe. But also you have the ability to look at, from SIPRO, a TDT. So this is you can overlay different TDTs on top of each other, and you can see whether they're all time aligned or if there's one particular trace which is shorter, has a less flight time than the others.
Great, thanks so much. And here is your question from Tom. Does it handle power awareness?
Oh, yeah, sorry, we just covered that one. So yes, the short answer is yes, it can, and the longer answer is that for DDR5, you need to be able to run transient to capture the characteristics of the jitter and amplitude noise, and then put that into the DDR bus simulation.
Okay, good. Okay, thanks so much, Stephen. This will conclude today's webinar. Join us next month for the continuation of our engineering education webinar series, and enjoy your day.